All right, I'm moving on. So the really key thing here is we want to solve problems of national interest. And so we've been working hard in this project to get applications ready to go, and they are on the system. And if we're successful, they're not only utilize the system well, but actually solve some problems. And so this is just a laundry list of a lot of ifs here. We're not claiming we're going to solve all the problems, but we're going to have technology that's going to help us address these problems of national interest. I think worldwide interest in many cases as well. So I'll just let you read a few, and I'll take you through a few examples. I added a few just this morning in terms of kind of where we started, sort of then and now. So 7 years ago, we started in earnest in this project. I'm going to move pretty quickly here. So if you think about the first three mover exascale systems in the US, we've got Frontiers on the floor, Aurora is being delivered as we speak, and El Capitan very soon. And so we've been working hard to get ready on day one to deliver and deliver applications and go after these problems. It's been, at least for Oak Ridge, this has been a decadal effort to deliver these systems. They're really, first of a kind, serial number one systems. And so as probably most of you are aware, we've been certainly talking about exascale for a long, long time. In the case of kind of what you see here are sort of key milestones for delivering Frontier at Oak Ridge in fall of 21. And the Exascale Computing Project really started in earnest in really the fall of 17. I'll talk mostly about the Exascale Computing Project, in particular the software stack and the apps, but it's really been a community-wide long-term effort. So if we look at Frontier, I sort of highlighted in blue my favorite parts of the system. It's got a lot of peak flops, and it's double precision flops. I would have guessed the footprint many years ago would have been much larger. I think the main thing here, and because of investment with US HPC vendors, it's kind of, we believe it's useful, and affordable now, in particular the power consumption. But a decent amount of memory. As an application person myself, we'd always like more than 9.2, but not bad. A lot of non-volatile memory, which I think we're still learning how to use. I think we still have a lot of work to go there. So 4 terabytes of non-volatile every node, and then a terabyte of memory. So there you see it's a 4 GPU system, and we'll talk a little bit more about the evolution there. So here's the node, and I think the cool part for me is it's fairly coherent memory. I'll say fairly because it's not quite. Each GPU is constructed by 2 GCDs, and you'll see a little bit of memory bandwidth difference depending on where you access. Yeah. No, Cassini is a Cray design, or now HPE design. Yeah. So I will say something about the Cassini. The nice things here is being able to go GPU to GPU. So each GPU is connected to a NIC Cassini, and so we can go from GPU to GPU. There's some magic underneath there in the software in terms of MPI, but also one GPU or one CPU can use all the NICs together. And so kind of the newer parts of the system, really the Slingshot and Slingshot NIC. But that's the basic design. And from a machine learning training point of view, with the Lustre file system, probably a little under provisioned. There are arguments that probably viable that a system like this might need about 100 terabytes per second for adequate training. The point is, if we learn how to use the flash well, we might be able to get close to that. So there's still work to be done in terms of fast I/O. But lots of, I didn't mention, but if I go back, over 700 petabytes of storage, and the Summit system has another 250. So as a center, we've got about an exabyte of spinning disks. So one of the goals here was to make these machines a little more affordable. So the goal was try to beat 20 megawatts per exaflop. And here you see that the investment, actually Jim Ang's here, and he started this Path Forward program where we invested heavily with HPC vendors to really go after 3 or 4 of the challenges to deliver a system like this, and one of them was power aware. So we're able to, with Frontier, we're able to drop below the 15 megawatts per exaflop, and so we have a nice standard PUE of 1.03. Let me say a little bit about now, a lot more about, the Exascale Computing Project. It's a large project in the Department of Energy, and really for the first time, at least since I've been around, we kind of have an intense software development effort in parallel with the hardware. because often the software lags by years and by capability. So this has been nice to have these two things going in parallel. So that's been quite unique. Large program, lots of researchers involved. The 6 of the 17 DOE labs that have historically been involved in HPC deployment were asked to lead the project. So our DOE sponsors were quite generous in holding folks like myself accountable and letting us make decisions. So that's been really fun and also certainly challenging at times. One of the things that we've seen at Oak Ridge and in the community really since, over the past now 10, 11 years is accelerated node computing is here to stay. And I'll define an accelerator as a piece of hardware that's really designed to accelerate certain floating point operations. So we started back in Oak Ridge with Titan in 2012, and that was a 1-to-1 GPU ratio. And I remember when we were making a pitch for that system, it was really high risk. Frankly, I think we had just a couple of codes able to run on the first sort of version of Kothe at the time, and really see quite an evolution in our ability to exploit these technologies for traditional PDEs as well as obviously machine learning. So there you see kind of the evolution. And when ECP started, we had a fair amount of community experience in kind of a single GPU and a single vendor. And so when we moved into the Summit, now we're talking about a kind of a 3-to-1 ratio, still NVIDIA. I didn't mention on the slide before, we've got different types of GPUs now, which I think has really been very good for the community. And with Frontier now, we are 4-to-1. And so there you see kind of the differences. And with our applications, we've had a nice sort of progression in how we work and how we develop. One sort of obvious and maybe sobering fact is if you, let's take Summit for example, if you don't use the GPUs, you're using it's about a 6 petaflop system, so you're kind of looking in the rearview mirror 12 years. So you really need to be able to use the GPUs because nominally 3 to 5% of the floating point operations are just on the CPUs. So you've got to be able to, well, we're really gone from using the GPUs to really being resident on the GPUs for most of the applications. So over about a 6-month period in 2016, we worked with our Department of Energy sponsors to carefully select the first mover applications. There are 24 of them here, but frankly, we feel like we're going to need to, and hopefully the proof will be in the pudding. We'll be able to lower the barrier for hundreds of other applications to really move here somewhat seamlessly. And in this case, each one of these applications is a strategic alignment with the Department of Energy program. We interacted with 10 different offices. And in some programs, there are 3 or 4 applications, others are just 1. And so it wasn't easy to down select based on time and scope. But here you see sort of I'll call it the challenge problem. You don't know what the app is per se or the community is, but these are the problems that they're tackling. Because we're a project, we have metrics, and again, be careful what you measure because you'll improve what you measure, but most of our metrics are really around showing you can address a particular problem. In some applications, and I'll mention that, also have performance metrics. So started with a lot of code, a lot of different projects. There were some fairly mature code, and also in some cases really just prototype. The selection wasn't based on risk. We had some high risk selections. So it would have been easier to go after low risk apps, but we went after the apps that were really important to Department of Energy. In some cases, they were very, very new and non-traditional HPC apps. This is an eye chart, and I'll leave it behind just so you can kind of get a sense of, for each application we negotiate what we call the base challenge problem. That's sort of just, a passing grade, and then a stretch challenge problem. Here you see the list of the base challenge problems. And overall, these problems could not be simulated without having an exascale system, so they require memory and compute power greater than petascale, greater than Summit. And also had specific risks and challenges. Each application team was kind of an eclectic mix. So as I mentioned yesterday, computer scientists, computational scientists, domain scientists, mathematicians, and each team had its own unique plan. In some cases, I think there were a few cases where basically the model was pretty much set. It was just a real heavy software re-architecture redesign, but in most cases the models and the algorithms evolved really in parallel with the overall software work. So again, the ones in green really had to show that they can demonstrate, they can simulate the problem, but also had a performance metric. In this case, 50x relative to 2016. That's kind of somewhat of a nebulous choice. It was really a peak-to-peak ratio, when in fact most of our apps really scale more with memory bandwidth. So what have the teams done? Basically, it's certainly not just port, but even porting, if you haven't run on GPUs yet, does require rewriting and reordering loops, memory coalescing, constructing a bunch of non-divergent, ideally small kernels. But the numerics in the models also adapt. In this case, particles are now more attractive. Certain algorithms were totally, sort of abandoned, and new algorithms came on board. And I'll give you some examples here. So, like I said, what we've gone from really in less than a decade is really now moving to where we have the compute power and for the most part the memory to just be GPU resident. And so instead of doing a lot of device host interactions, get down on the GPUs and stay there as much as you can. Okay, and that requires a fair amount of refactor and redesign. In many cases, going after totally new algorithms. So this is a 3-year. Just a sense of what happened over 3 years on Summit. Summit at Oak Ridge, 200 petaflop system, has proven to be a tremendously successful system, and our performance on our applications have far exceeded expectations. So you see the 50x bar there. It looks like we kind of cheated and maybe sandbagged a little bit, but we didn't plan this. In some cases, there was nascent code in EQSIM and Exalt, and I'll say a little bit about that really just hadn't been looked at in many years, and just was in revisiting and rethinking. In this case, loop ordering, loop coalescing, et cetera, made a huge difference. So these are the applications that are on the hook for 50x. It doesn't mean they're done, because they got to show that they can do this on Frontier. So this is basically give you a sort of a 3-year sense of what things had happened over 3 years. Andrew Siegel at Argonne National Lab constructed this. I really like this because of the applications in terms of moving to GPUs really made different choices. And so you can think about productivity, portability, and this is really kind of subjective. But if you think about that axis versus your control, the applications have made different choices. You can adopt a high-level framework and just live in that framework, live on top of that framework, and defer all the ugliness and all the complexity to the framework. And that allows you to be potentially fairly productive and fairly portable. Or you can program down in the metal, have total control, and that brings you down to just native CUDA, HIP, or SYCL. So the applications, we didn't force it. The applications made their own choice. We didn't really mandate a particular programming model, but what we saw was some nice abstractions really evolving. In particular, Kokos and Raja, and Kokos in particular from Sandia, about a third of our codes have adopted that abstraction layer. And one interesting thing, I don't have a slide here, is you can go to Copilot, and Copilot knows about Kokos. So what we're seeing is, these abstraction layers might be able to be written at least first start with some of these foundational models. So one choice we made that I'm going to claim really has paid off is buying into motifs, and this came from Phil Colella back in '86, '87. This is the 2006 version, where most applications use a surprisingly small number of motifs. So if you dive into these motifs or common patterns of communication, computation, try to make those scream on this hardware, you might be able to have economies of scale and impact multiple apps. So that's a choice we made, and it was a bet. I think it's worked out well. They're called co-design centers more because of a legacy name in the Department of Energy, when really what's going on here is co-design kind of down through the software stack. This really isn't co-design down in the hardware. In ECP, a lot of what we've done is really hardware-driven algorithm design. In this case, these are the choices we made, and really a lot of the choices were based on more traditional PDE solvers, because that was our app base. I'm going to take you through a few examples. So adaptive mesh refinement, really led by John Bell out of Berkeley. This has been given us a real big return. There you see 6 of the ECP apps really are living in this environment. So it's not just patch-based mesh refinement, but how do you do linear solvers on these patches, across patches? How do you push particles? How do you bring in embedded boundaries? And so here you see underneath the covers, you see various abstractions. So these applications, for the most part, are just living on top of this layer, and it's kind of a really new middleware layer. And underneath the cover, so to speak, all the challenges of porting are taken care of. So there's a risk involved here when this technology has to be there, has to be kept up to date. And so, certainly applications and make choices on this. So about a month ago, we had an annual meeting in ECP, and we asked each team to sort of give us a table of then versus now. And I'm just going to cruise through some examples pretty quickly. But you see here in the case of AMRX the evolution in the software and in the technologies. And basically there was no real embedded boundary capability. A lot of homegrown geometric multigrid, and so a lot of work on solvers, moving to algebraic in some cases, adopting other technologies, being able to push particles. So been a real boon here. I think this is a piece of technology that's going to be around for a long time. Here's an example of an application that really built on top of AMRX, and that's ExaWind. Well, in this case, and apologies here, you can obviously tell I would cut and paste directly from the PDFs here. This is led out of NREL, and so here you see the approach then and then now. And this is a interesting application that has a finite element unstructured mesh following the turbine blades, okay? And that's NALU wind. And then you've got AMR wind, which is the background flow through the wind plant, and that's based on AMRX. And you've also got a weather code, in this case WRF, but they're bringing in AMRX into WRF. So you got 3 codes here that are coupled together. The challenge problem was to do 4 turbines fully blade resolved, when really what they want to do is kind of 50 turbines. Because the current data shows that these wind farms can lose 20 to 30% of potential energy just by buffeting back and forth and interactions with each other. So the challenge here is really understanding the interactions turbine to turbine. So that's been a nice development. Let me move to another co-design center or a motif, and that's unstructured mesh finite element. This also hits a number of our applications. And this is a project known as SEED, so it's just not unstructured meshes, but generally you have finite element discretization. In this case, as we're seeing our systems become kind of more and more starved for memory, but have more and more compute, so flops are basically free, so let's go high order and finite element, use less mesh. So that's what the approach has been, 6th, 7th, 8th order and less mesh. And so that's really kind of adapting to the hardware. In this case, the SEED effort, Bozanio Kothe at Livermore, you see basically there were some early successes kind of built within one given code. Now move it out into a library, which is MFIM and LiveC seed, and be able to support all the matrix vector operations associated with finite element discretizations. Have a bunch of bake-off problems, community problems, and integrated into several applications shown there. So again, these are traditional high-order finite element simulations now can really build on top of this motif-based center. We've seen a lot of other codes outside of ECP actually adopt this center as well. Here's an example, small modular reactors. You've got thermal hydraulics flowing up through the core of a reactor. In this case, an unstructured mesh code known as NEC 5000 evolved to NEC RS, solving the fluid dynamics. And then a Monte Carlo code, full core, continuous energy Monte Carlo. And the Monte Carlo effort is quite interesting because Monte Carlo is embarrassingly parallel, so each particle can kind of go on and do its own thing. But if you fill up a GPU with a bunch of particles, you might have a couple that need to have 200 collisions before they'll be absorbed. And when most maybe will be absorbed or fission or whatever after a few collisions. So if you go for particle-based statistics, GPU utilization is going to suck, frankly. But this particular application went to event-based statistics, grouped particles together in like bins, so that all the neutrons that are going to scatter, fission, absorb are put in bins, and the team got tremendous GPU utilization. Really being able to push trillions of particles, which if you get the cross sections right, pretty much nails the answer for neutronics. Another one, particle-based motif, and most codes do use particles, some discrete version. So the Center for Particle Applications is known as COPA. I think if you have a project known as COPA, you're going to have a library known as Cabana, okay? So in this case, the Cabana library pushes particles through unstructured to structured meshes, maps particles to mesh to particles, and has a lot of functionality underneath it. And a lot of particle-based methods use FFTs, and so you can see combinations of motifs here. We've actually spent time on FFTs as well. So in terms of who's using COPA, well, actually this is kind of then and now. A number of applications have really been embracing the particles. So we've got particle in the cell applications for plasmas. We've got particle-based applications for electrodynamics, both metals and soft matter, and in many cases, tremendous performance speed up. The XGC code, which is a gyrokinetic particle and cell code, was entirely in Fortran, and began to bring in the Cabana library and infuse more C++ and get a lot of performance gains as well. So at the beginning of ECP, I was really skeptical we could actually come up with a particle library because it tends to be sort of embedded in the application, but it's worked out pretty well in terms of bringing in, being able to abstract the particle-based efforts and then have them available. Another one, really, one of the things we're after is additive manufacturing. It's really ubiquitous everywhere, and maybe you think it's a solved problem, but for high-spec metal alloys, it's not. You've got kind of 50% rejection rate for high-spec metal alloys. You'll get porosity you don't like it at microsegregation, et cetera. So we're after really fundamental simulation of the 3D printing process itself, which involves melting, solidification, non-equilibrium melting, solidification, residual stress, porosity, very, really complicated. So the exam effort really has gone from not really having a code base to now simulating additive manufacturing at multiple length scales. And the idea is to be able to predict the printed microstructure so that you can design the process to get the microstructure you'd like. 3D printers have about 12 parameters that you can adjust on the fly. So ideally, you'd like to train a machine learning network to adjust the 3D printer on the fly. Things like intensity, speed, et cetera, the laser or the E-beam. Oops. Another application that actually won the Gordon Bell Award last fall is WarpX. In this case, it's a full particle and cell application, full Maxwell solver. And one interesting thing at the top here is, as a result of this development, you've got kind of an evolution of a code base here going from Warp to WarpX, but then other applications are building on this outside of, this is really for accelerator physics and accelerator design, but other applications are built on top of this for microelectronics and other sorts of efforts. But this is another example of kind of moving from Fortran more to C++. Again, we haven't forced it, but a lot of applications have made that choice to begin to move, a lot of Fortran-based applications to begin to move in that direction. And then in this case, the challenge problem was a multi-stage Wakefield accelerator. And so basically you need to move in the frame of the laser or the E-beam and be able to go from kind of single stage to multi-stage. So quite an onerous challenge problem. This is an example of the code base in 2016 and then kind of late fall. And so you see the evolution in the overall algorithms and the physics. And one of the interesting things here as well is following its figure of merit. So basically the ratio of its performance is measured in kind of particles per second is sort of a metric of science work rate. And you see it's the figure of merit in this case. Over 500x was actually recently just shown on Frontier. So the Gordon Bell winner that ran on Frontier, and there you see the pretty pictures. It has a lot of other application possibilities outside of accelerator design. So Jean-Luc Vey and his folks, this is really an international collaboration with CEA and other institutions. Very, very nice development. I'm going to now move to molecular dynamics, and as everyone probably appreciates here, you have the curse of small time step, and so being able to move to larger systems is easier in MD, but really, really difficult for fundamental long time scale, millisecond or second integration rates. And so the goal of this method is to really be able to move into longer time scales. And so how do you do that? Well, let me go back. You really have to use accelerated MD, in this case, replica dynamics, where you're basically simulating, say, a couple thousand different instances together. And statistically, when you get a particular statistical event, you stop the simulation, and then you fire off another few thousand, and basically your time step is the sum of the time steps of the individual replicas. So replica dynamics is how you can get around for certain systems the short time scale constraint, and basically what you do here is now you fire off a whole bunch of LAMP simulations in this case. The interesting thing too with having local GPUs and lots of free flops, you can do quantum-based potentials on the fly with a code called Latte. In this case, it's DFTB based assumptions. So basically now you have quantum-based potentials on the fly with hundreds or thousands of workers. And this led to a capability known as parsplice, which actually we found during COVID was also useful for soft matter MD codes like NAMD, Amber, and GROMACS. So it's a nice environment that I think is going to have legs outside of just metal alloys, which has been our focus. And again, this is the effort known as Exalt. I think the thing I want to point out here is this team really moved into machine learning-based potentials, being able to use DFT simulations and data to train to get good on-the-fly potentials. And so they brought in machine learning as a way to augment and accelerate their workflow. I'll say a little bit about machine learning. In ECP, we're doing more than dabbling in machine learning, but it's not a 50% of our scope. It's probably 10 or 15% of our scope. So we've infused more, I think more trying to augment and accelerate existing workflows. In this case, we have a project known as ExaLearn. Everything's Exa, okay? I didn't come up with these names, but in this case, this project's really focused on kind of 4 what I call pillars where you can really, I think, accelerate and augment workflows: surrogates, control, design, and inverse. In this case, just giving an example of surrogates, and we've used cosmology. It's Salman Habib's effort at Argonne, evolution of the universe. And really before this effort got started, we really were not able to come up with good surrogates. And using GANs and being able to have the GAN method scale and be statistically relevant, statistically accurate has been quite an effort. The L-band code is a scalable machine learning code out of Livermore, and they've been able to come up with good surrogates. And so this is really promising for all kinds of reasons, not the least of which would be sensitivity analysis and uncertainty quantification. So again, what we've done here is we've really tried to tackle some very focused use cases rather than come up with general capability. We're not trying to rewrite frameworks or write a new framework, but use existing tools and technologies to accelerate our current workflows. But one question we've been asked is, how big of a model could we train with Frontier? And initial analysis says maybe 10 to the 14 parameters, and we wouldn't want to do it just for the heck of it. We want to do it for science. And so we do have a team. It's called the 9 Yards Project, and my father loved cliches, and he'd always say the whole 9 yards, and so we just took that. So this is a project that's really looking at how large a model can we train, and we think if we just live in the HBM, we might be able to train kind of a 10 to 14 parameter model. And in this case, we're going to go after certain material science problems and also polymers. So hopefully in the months to come, we'll be able to kind of roll out some examples of what we think we can do. But I will say, just doing big models isn't always the best. Sometimes you overtrain, but I do like this paper, Beyond the Imitation Game. And it's about 50, 60 different benchmarks for language models, and I enjoyed reading it, but I like this one in particular. It shows the evolution of trained models for different numbers of parameters. So in this case, what does this emoji describe? A couple million, even into the billion, and you don't get a lot, but you get 128 billion, you get the right answer. We got to be careful here because this is just kind of a fun problem, but the point is I think as a community, we need to have some really tough benchmarks that really break these models and help us understand just where the cliff is in terms of training. So this I just found kind of amusing. On the AI front, I have been involved recently with Rick Stevens and colleagues to take a close look at what's the efficacy of this area for science. So there have been a number of workshops even back in 4 or 5 years ago that deliver some initial reports, in this case looking at all the programs in the Department of Energy and where can AI be infused in the current workflows and where can it really make a difference. And more recently we're working on a new version, should be out in the next month or so. It really was a result of 3 workshops last year, I think, and Karen and many of you were there. The focus here is really to look look at these kind of 6 different themes, okay, not surprisingly, properties, inference, and inverse design, autonomy, surrogates, AI for programming. We've actually seen, CodePilot, for example, knows a lot about Kokos and Raja and can write some pretty decent code, which has been really a pleasant surprise. Mike Carew at Sandia is looking a lot at this. Prediction and control and foundation models. And so we've got some target problems in each of these areas, and working with our DOE sponsors, hope to get some support to go after this area in earnest. So this report's coming out very soon. Let me go back now to some what I would call non-traditional applications. This is stochastic grid dynamics, and this is a tough one. And apologies, I had just copied and pasted a poster from Chris Oman at PNNL. But in the U.S., we have three interconnects: the western, eastern, and western Texas. Yeah, Texas has its own interconnect, as Karen knows, and eastern. And so you see, even since ECP, we've kind of moved to maybe do more of a decent job at the western interconnect. And this is a security-constrained optimal power flow. But just a couple of problems that we're looking at. One is the kind of the under-frequency problem. In the Texas, we had problems in the Texas grid with several gas plants went down. The frequency went from about 60 to 59.7, which is really bad. And so what we're doing with this effort is simulating the under-frequency problem by just knocking off several energy generators in the simulation, see what we need to do to recover. And this certainly has a lot of machine learning potential, but right now we're using differential algebraic equations, which are really hard to solve. They involve mixed integer programming, a lot of really difficult nonlinear optimization. And so some new libraries known as HiOp and Exago are coming out. In this case, the voltage and reactor power event, that's the under frequency, but also looking at the intermittency of wind, being able to plan to bring wind on. What if you have a hurricane? You might need to shut things down, and so you don't have the wind, et cetera. So being able to look at certain scenarios, extreme weather and under frequency. And so this is a new application, really wasn't there. Building a scalable application is important to be able to do high fidelity interconnect simulations. Another one that's new, Kothe Yellick went after genome assembly. And before ECP started, there's a code called HIPMER that was really a single genome assembler. We started to rewrite it in UPC and then moved it to UPC++. But the way cool thing about this particular effort is only a couple terabytes of data could be analyzed and assembled. It took many, 1,800 hours, but now she's been able to assemble up to 30 terabytes. The goal is 50 terabytes in, literally hours. And it's become the production assembler at JGI at Berkeley, which is really quite a remarkable accomplishment. And so this requires a lot of hash tables. There's a lot of indirect addressing. Didn't look like it was amenable to GPUs at all, but with Kathy's talent, her team really able to get good utilization. And so also she's moved on to protein clustering and some really interesting problems. So this is an example of an application that has a lot of applications in human health, but also was driven by the microbiome in our BER program office in DOE. This is the one I dropped in just this morning, realizing we have lots of weather folks here. So I've dabbled in this area many years ago, porting an ocean code to the connection machine, actually. So I know maybe enough to be dangerous here. But here you see kind of the baseline model of where we were at the beginning of ECP and kind of where we are now. I will point out that being able to simulate kind of 2 to 5 years per day on Frontier still means that it'll take sort of 20 days for a century simulation. And we really need to do ensembles of century simulations. So we really need to be able to do 10 or hundreds of these simulations daily. And so this is where, this is a real compute driver, but also where potentially some trained models can get us there more quickly. But I will say, one of the things the Department of Energy did is they forked the code base away from CESM. E3SM is a code base. It's a DOE code base. It's really moved off in exciting directions. And what we have funded mostly in ECP is porting the atmospheric dicore in particular onto GPUs, and also the superparameterization model as well. Not being able to now do 3 kilometers resolution instead of 15 or 20. maybe even sub-kilometer for regional simulations. The non-hydrostatic solver is now the base solver instead of hydrostatic. And so been a lot of interesting developments in the E3SM model. Certainly the recent events in Turkey, Syria has made us think a lot about the importance of earthquake simulation. And Dave McCallan and his folks, using a code called SW4, have been focused, not surprisingly, on the San Francisco Bay Area. That's the SFBA over there. But it turns out that you need to be able to resolve 5 to 10 hertz frequencies, and that requires a lot of temporal and spatial resolution. And that's where a lot of the coupling occurs. And often the coupling occurs at kind of 4 to 5 story buildings. And so we saw a lot of that in Turkey and Syria. So really going after being able to do fully coupled simulations coupled with the structural elements as well. In this case, even though they're post-dictions, the post-dictions can inform risk-based sort of earthquake-hardened designs. And so I think Dave and his folks are looking to see if they can get data for the recent events and be able to help understand kind of what happened and why. But just an example, being able to really go after, because of moving on to GPUs and with the Exascale systems, being able to resolve 10 to 20 hertz, which is where you need to go, where it's really been a game changer. I'll close by saying a little bit about the software stack, okay? And this is an example of Jack Dongera's effort, known as Clover, now led by Hartwig Angst. And so, just sort of most of the community is probably very well aware of Scale-a-Pack, and this is kind of a nice summary of where that functionality was in 2016. And now you have software library accessing, I forgot the SLATE acronym, but in any case, really covers Scale-a-Pack and BLAS++ and LA-Pack. And so being able to move this entire, really very important community functionality to evolve it, move it over from Fortran to C++, and of course port on the GPUs. So here's an example of the Scale-a-Pack effort. And one thing that Jack's really focused on that's really been pleasing is FFTs and benchmarks for FFTs. I think we sometimes forget as a community that most of us kind of use 1D FFTs when we need 3D, and I think the community hasn't really focused as much on FFTs. And so his effort, known as Hefty, is shown here, and making good progress for fully sort of in GPU 2D and 3D FFTs, and not sort of cheating by stacking up 1D. There's also an effort known as FFTX at Berkeley that's going to be integrated into this, and so a lot of codes require effective FFTs. So this has been another effort that's part of the Clover effort. And then Ginkgo is Hartwig Angst's solver. And what we're finding for a lot of our applications is we really need fast on-node linear sparse solvers. And in this case, we've moved a lot to batch sparse solvers, where we'll throw a decent-sized matrix to every GPU, basically being able to recast the problem into a bunch of smaller problems. So Ginkgo is really a fast Krylov solver on node for the most part. That's been a real game changer for a lot of our efforts. I will close by saying we've worked to package a lot of our software products within one stack known as E4S, Extreme Scale Scientific Software Stack. We've been releasing it for about 4 years now, every 3 months. So I encourage you to go to e4s.io. Certain, I think, black holes for people's time, such as building code and packaging code and releasing code, have really been helped by the SPAC package at Livermore. And so I encourage you to go there, where we do bring some industry frameworks in there as well. And so that said, I've got apologies for the words here, but I'll just leave them here and close. Thanks for your time and attention.